Hello everyone, and welcome back to another tutorial video. In this video, I will be covering problems that require you to perform a partial fraction decomposition. And what I have done for you right here is I've written up the two primary rules. You can find these in section 7.3 for performing partial fraction decompositions. Again, partial fraction decomposition, I know I've said that quite a lot already to start this video, is really just an algebra trick. You don't need any calculus, you don't need anything special from this course, but it is something that can be relevant in many situations, including when we're working with Laplace transforms. So these two rules address how to deal with different types of denominators. Rule 1 deals with linear factors in the denominator, and it says that if you have a factor in the denominator that is linear and has a power of n on it, or multiplicity n, both terms mean the same thing, then that term will get decomposed as a1 divided by, say s minus a. Let's say if that's the factor, a1 divided by s minus a plus a2 divided by s minus a squared, and so on and so forth, all the way up to an divided by s minus a to the n. So we have a bunch of constants in the numerators being divided by that factor, that specific factor that we're working with, in the denominator that has its power increasing gradually until it reaches the multiplicity of that factor. Now for rule 2, we are working with irreducible quadratic terms. These are things like x squared plus 1, or various other quadratic-looking terms that can't be factored. And you can check, there are various ways of checking that a quadratic term cannot be factored, but the most straightforward one is probably just to try quadratic formula, and if it gives you a solution that is complex or imaginary, then you know that it is irreducible. Alright, so if you have a factor that's irreducible quadratic, that's to the power n in the denominator, how do you decompose it? Well, you're going to have the same setup with that factor, a bunch of fractions with that factor in the denominator with its power gradually increasing up until its multiplicity. But this time in the numerator, instead of just a constant, we're going to have a1s plus b1 plus a2s plus b2, etc., plus ans plus bn, divided by first that irreducible quadratic term to the power 1, then to the power 2, then to the power 3, etc., up to the power n. Alright, I'm not going to keep these rules up on the board because they take up a lot of space, but I will be invoking them as I work through the problem. So let's move on to that. Alright, so for this first example, I'm going to go over a more full problem from the textbook, but that is going to be slightly simpler than this. But I want to go over a first example that just asks you to set up the partial fraction decomposition for the following function. It's 1 over s to the fourth minus 16, that whole denominator squared. I'm not going to go through the entire solution of the partial fraction decomposition for this guy, just because the part where you solve the system of equations would be very tedious. You would have 8 equations and 8 unknowns, and that takes a lot of time, and I don't think that that's particularly useful. I do think, however, that it is worthwhile to look at this guy just to set up its partial fraction decomposition. Just set it up, not actually solve the whole thing. So the first step, as always, in any partial fraction decomposition problem, is to factor the denominator. And you'll note that s to the fourth, that is a square, minus 16, 16 is also a perfect square. So this is an a squared minus b squared factorization that we have here. So 1 over s to the fourth minus 16 squared, you can see that this can be factored as 1 over s squared minus 4 times s squared plus 4. All that squared. And then s squared minus 4, this term here, can itself be factored once more in exactly the same way. And you'll see that we get here, we're going to have s plus 2 times s minus 2 times s squared plus 4, and this whole thing is going to be squared. And again, this guy just factors into this. So now we're going to how should we say, distribute out this squared in the denominator to finally get that 1 over s to the 4th minus 16 squared is equal to 1 divided by, we'll have s plus 2 squared times s minus 2 squared times s squared plus 4 squared. And you'll note that these two terms here are both linear, whereas this term s squared plus 4, this is an irreducible quadratic. There's various ways of checking that. First of all, you can see that s squared plus 4 is never going to be equal to 0. It will always be greater than or equal to 4, because squares are always positive. And another way to do that is if you plug this into quadratic formula, you will see that it will give you an imaginary solution, so you know it is irreducible. Okay, so we've got this factorization for the denominator. That's basically step 1 completed. And so we've noted that for all of these are all multiplicity 2. And that includes this irreducible quadratic term, because they're all being squared in the denominator. All right, so all I'm going to do with the rest of this example is just from here set up what the partial fraction decomposition would look like for this fraction here. All right, so we got our factorization of the denominator. We have s plus 2 squared times s minus 2 squared times s squared plus 4 squared. Now, as I mentioned, these first two terms are linear of multiplicity 2. That means that these two terms will use rule 1. This third term here uses rule 2 because it is an irreducible quadratic term. So let's set up what this has to look like. We would set this up as follows. I'll just write denom here for the sake of not taking up all the space on the screen. The first term, or the first two terms, would come from the s plus 2 term. And these would be a1 over s plus 2 plus a2 over s plus 2 squared. These come from rule 1 for that s plus 2 squared term. All right, then the next two terms are the same thing, but for s minus 2. So we've got a3 over s minus 2 plus a4 over s minus 2 squared. And once again, both of these terms come from rule 1 for s minus 2 squared. Last but not least, we'll have two more terms. We'll have a5 times s plus b1 over s squared plus 4. And then we'll have plus a6 times s plus b2 over s squared plus 4 squared. And these two terms, rather, come from rule 2 for s squared plus 4 squared. All right, that's it for this first example. Again, the next step after this would be to put this under a common denominator, to clear the denominators, and then to set up a system of equations and solve it. That is definitely feasible here, but it would take quite a bit of sort of work, and it would be quite tedious. So what I'm going to do now is I'm going to work out a more complete problem that is going to be a simpler, basically a simpler version of this example problem here. I wanted to do this example just to show how you would deal with things with higher multiplicity than just 1 in the denominator. All right, so here is the full problem I want to work through in this video. It is problem number 17. You can find it in your textbook. It's problem number 17 from section 7.3. And it asks you to find the inverse transform of the function capital F of s is equal to 1 over s to the fourth minus 16. So exactly the same denominator as I just went over, except without that squared here. And because this is very similar to what I just did, I'm going to go relatively quickly through the first two steps. Step 1 is to factor the denominator. And for this, we will get that f of s is going to be equal to, obviously this is 1 over s to the fourth minus 16. And this factors into 1 over s squared minus plus 4, times s plus 2 times s minus 2. So this factors exactly the same way as the last problem did, except without all the squares there everywhere. Okay, now step 2 is to set up the decomposition. And what we'd get here is that 1 divided by s to the fourth minus 16 is going to decompose as follows. We'll have a1s plus b1 divided by s squared plus 4 plus a2 divided by s plus 2 plus a3 divided by s minus 2. And again, this is rule 1 for that s plus 2. This is also rule 1 for that s minus 2. So both of these two used rule 1. And then this term comes from rule 2 for that s squared plus 4. Alright, we've now set up the partial fraction decomposition. So we're now going to jump right in and try to, figure out what all of those unknowns are going to be in the numerators. And to do that, every single time, once you get to this step, the following step is always going to be the same. And this is to put everything under a common denominator, or over a common denominator. And then we're going to clear the denominators. Alright, so let's go ahead and do that. This all just involves multiplying the numerators by everything that their denominators are missing. So at this point, what the denominators are no longer matters. So I'm just going to put this just the word denom in the bottom, because all of those denominators are going to be the same. Alright, our first term is a1s plus b1. And what does this need to be multiplied by? Well, it needs to be multiplied by s plus 2 and by s minus 2. And that's still going to be over the same denominator. Okay, now the second term is a2. And what does this guy have to be multiplied by? Well, this guy has to be multiplied by s squared plus 4, and it needs to be multiplied by s minus 2. And it, again, is over the same denominator. And the third term, which I will write down here, is a3. And this guy needs to be multiplied by, oops, that's not a 4. It's an s squared plus 4. And it also needs to be multiplied by s plus 2. And it, again, is over the same denominator as before. And because all of these denominators are exactly the same, we can go ahead and clear them all out to leave us with a much simpler looking equation. Here's what we're going to get. We're going to get, on the left-hand side, just 1. And that's equal to, on the right-hand side, we have a1s plus b1 times s plus 2 times s minus 2. Then we have plus a2 times s squared plus 4 times s minus 2. And then we have plus a3 times s squared plus 4 times s plus 2. All right, so we're done with step number 3. So what I'm now going to do, the next step is of course going to be to set up the system of equations from this, and then to solve that system of equations. We have 4 unknowns, a1, a2, a3, and b1, so we're going to need 4 equations in our system. Now, the first thing I'm going to do is I'm going to clear this board and rewrite what we just got. All right, here we go. I've done that, and so now we proceed on to step 4. And step 4 is to set up the system of equations. And to solve it. Now, there are several ways to do this. The method that I have mostly taught you guys in class is sort of a brute force method that is very important to be comfortable with because it is very applicable in other situations as well. And that method was, of course, to multiply this whole thing out, and you're going to get some s cubed terms, you're going to get some s squared terms, you're going to get some s terms, and you're going to get some constant terms. And then you're just going to match up those terms on the left and the right hand sides. And that should be enough to set you up with 4 different equations. That technique is called identification of coefficients. It is very good to know. It's totally cool for you guys to use that on an exam. But I thought that in this video, I would go over a different method that also works in this case. And this method is to actually just plug in 4 different values of s into this equation to give us 4 different equations that will result from that. This method can be pretty nice. First of all, it sort of clears out all the s's immediately. And second of all, if you pick sort of intelligently your values of s, you can sometimes clear things out pretty significantly and make your life pretty easy. So what I'm going to do here is I'm going to plug in the following values. I'm going to plug in s equals 0. I'm going to plug in s equals 1. I'm going to plug in s equals 2. And I'm going to plug in s equals negative 2. Now, I do want to note that any 4 different values of s should work unless there are perhaps some very strange situations in which that may not be true. But for the most part, if you take any 4 different values of s here, that will give you 4 different equations, and you should be good to go. But I did pick at least 2 of these pretty carefully. I picked s equals 2 and s equals negative 2, specifically because they're going to make some of these terms 0 and simplify our life quite a bit. So let's see how that works out. All right, so first off, in the first line, when we plug in s equals 0, what are we going to get? Well, we're going to get that a1 times s is just 0, so we're going to have b1. And that's multiplied by 2, and then multiplied by negative 2. And then plus over here, we're going to have a2 times 4 times negative 2. And then we're going to have plus a3 times 4 times 2 is equal to 1. And this guy I got from plugging in s equals 0 here. Okay, so for the next one, I'm going to plug in s equals 1. Let's actually not get to that one. That's by far the messiest one of these. So next up, let's plug in s equals 2 here. And you'll see that when s is equal to 2, all of the s minus 2 factors become 0, and they clear out completely. So for s equals 2, we're going to get the following. We're going to get that whole first term cancels out, that whole second term also cancels out, and we're left with a3 times 4 plus 4 times 2 plus 2 is equal to 1. And again, this is what you get from plugging in s equals 2 here. All right, for the next one, I'm going to plug in s equals negative 2, and we're going to have a similar type of cancellation. This time, the first and the third terms are going to go away, and we're going to be left only with the middle one. What is that going to give us? It's going to give us a2 times negative 2 squared plus 4 times negative 2 minus 2 is equal to 1. And again, this one was obtained from plugging in s is equal to negative 2. All right, last but not least, we're going to plug in s equals 1, and this is going to give us the length here of the the lengthiest, I should say, even, of the 4 equations here. And we're going to get the following for the last one. We're going to have a1 plus b1 times 3 times negative 1 plus a2 times 5 times negative 1 plus a3 times 5 times 3 is equal to 1. So you can see this is the only one of our 4 equations, in fact, that features all 4 of the unknowns. All right. So the nice thing about this system is that when we plugged in 2 and negative 2, we got a lot of cancellation. And so these 2 equations right here can both be solved rather quickly. So these 2 are going to give us, the first one gives us that a3 times 8 times 4 is equal to 1. And that's going to give us that a3 is going to be equal to, I believe, 1 over 32. And the other one is going to give us that a2 times 8 times negative 4 is equal to 1. And therefore that a2 is equal to negative 1 over 32. All right, now we can plug these in and get some more work done in the next ones. So next, let's tackle that first equation. And let's plug in our values of a2 and a3 into this to get that we're going to have negative 4 times b1 minus 8 over, this is a2, negative 32. And then we're going to have plus 8 over 32 is equal to 1. That's going to give us that negative 4 times b1 plus 16 over 32 is equal to 1. Now, of course, 16 over 32 is equal to 1/2, so this gives us that negative 4b1 is equal to 1/2, and that's going to give us that b1 is equal to negative 1 over 8. All right, there is only one equation left to go, and so let's tackle that one if we can. So this guy, we're now going to plug all the things that we know into this one. So now we're going to get that a1 minus 1 over 8 times negative 3 plus a2, so rather than plus, that should be a minus 1 over 32 times negative 5. And this should be plus 1 over 32 times 15 is equal to 1. All right, I'm going to clear this board, write down what we've got, and continue from there. All right, so this is what we've got from what we had before. We have a2 is negative 1 over 32, a3 is 1 over 32, and b1 is negative 1 over 8. And then the last equation that we have is a1 minus 1 over 8 times negative 3 plus 5 over 32 plus 15 over 32 is equal to 1. Now, of course, this can be simplified quite a bit already. Still have this guy. And then this is plus 20 over 32 is equal to 1. All right, 20 over 32 can be simplified. Both the numerator and the denominator are divisible by 4. So this now gives us a1 minus 1 over 8 times negative 3 plus 5 divided by 32 is, of course, 4 times 8. So here we have 5 over 8. and then this is equal to 1. All right, a little bit more work to go here. You still have a1 minus 1 over 8 times negative 3 is equal to 1 minus 5 over 8 is, of course, 3 over 8. Okay, so now we can cancel out the 3's, but don't forget the negative sign. And this will give us now that negative a1 plus 1 over 8 is equal to 1 over 8. And this, of course, gives that a1 has to be equal to 0. All right, we have solved our system of equations. We have gotten our 4 unknowns solved for now. And this will allow us to set up the partial fraction decomposition. In other words, we have now determined that our f of s is equal to 0 times s plus, or rather minus, 1 over 8 over s squared plus 4. Plus, or rather minus, 1 over 32 over s plus 2 plus 1 over 32 over s minus 2. All right, let's rewrite this to simplify this just a little. We've gotten that f of s is equal to 1 over 8, or negative 1 over 8 rather, times 1 over s squared plus 4. Minus 1 over 32 times 1 over s plus 2 plus 1 over 32 times 1 over s minus 2. Okay, we are done with the partial fraction decomposition. If all you are coming to this video to look for is the partial fraction decomposition work, you can stop here. That's done. However, this example problem that I'm going over asks us to use this partial fraction decomposition to find the inverse transform of this function capital F of s. So let's move on to step 5. Find the inverse transform. And by linearity, you will see that the inverse transform of f of s is going to be equal to negative 1 over 8 times the inverse transform of 1 over s squared plus 4 minus 1 over 32 times the inverse transform of 1 over s plus 2 plus 1 over 32 times the inverse transform of 1 over s minus 2. Getting a little bit cramped there, I apologize. All right, so for the final time in this video, I will now clear the board and move what we have to the top and finish out this problem. Okay, now luckily 2 of these inverse transforms are pretty easy to find. You can read them off directly from the table in 7.1.2. We see that the inverse transform of 1 over s plus 2 is going to be e to the negative 2t. And we'll see that the inverse transform of 1 over s minus 2 is equal to e to the 2t. Now the problem comes with this first term. We have 1 over s squared plus 4. That does not show up in that table. However, you will notice that there is something very similar that does show up. In the table, you will see that the inverse transform of 2 over s squared plus 2 squared is equal to sine of 2t. Now this is quite similar to that first term that we have. And so we simply have to notice here that 1 over s squared plus 4 is equal to 1/2 of 2 over s squared plus 2 squared. So in other words, the inverse transform of 1 over s squared plus 4 is going to be equal to 1/2 times sine of 2t. All right, now we plug this all in, and we will get that the inverse transform of f of s is equal to negative 1 over 8 times 1 over 2 minus 1 over 32 times e to the negative 2t plus 1 over 32 times e to the 2t. And simplifying this all one last time gives us that this is equal to negative 1 over 32 times e to the negative 2t plus 1 over 32 times e to the 2t minus 1 over 16. And this is the final answer to this problem. All right. Hopefully this made some sense. Hopefully you guys saw how the partial fraction decomposition process works. Hopefully you saw how I worked out these inverse transforms by using the table of reference, the table 7.1.2. But as usual, as always, if you have any questions, please feel free to get in touch, shoot me an email, and I will see you guys in the next video.